Hey guys, welcome to question MM406 of the Maths Methods Fortify study guide. So Brittany owns an apple orchard of 4,000 trees. The height of a tree in her orchard is a random variable which is normally distributed with mean 4.6 meters and standard deviation 30 centimeters. Part A says, how many trees are taller than 4.8 meters? Give your answer to the nearest whole number. Alright, awesome. So the first thing to recognize is we're obviously dealing with normal distribution. It tells us that the variable is normally distributed, so we need to treat that as such. So I like to draw a little normal distribution graph because it helps me keep track of what's happening. We know that the mean is 4.6. We know that the standard deviation is 30 centimeters, which is the same as 0.3 meters, right? So we have 4.9, 5.2, 5.5, 4.3, 4.0 and 3.7. Awesome, so our mean is 4.6. Now, we're looking for how many trees are taller than 4.8 meters. So we know the total amount of trees, but we're not sure how many are taller than 4.8 meters. The only way we can work this out is to figure out the probability of any given tree being taller than 4.8 meters and then apply that to the total 4,000 trees. And you'll see what I mean by that in a second. So we're looking for the probability that any given tree is greater than 4.8, which is this area here, right? So the way we find that is using our normal CDF. So open up your normal CDF in CAS. I think mine is menu 552. And it'll ask you for four things. Ask you for lower, upper, mean, and standard deviation. So our lower is 4.8. Our upper is infinity, our mean is 4.6, and our standard deviation is 30 centimeters, which is 0.3. Okay, so don't mix up your units because that'll stuff it up. What we want to do from there is just click enter, and that'll tell us that the probability that any given tree is greater than or equal to 4.8 meters tall is equal to 0.2525. That's actually our first mark. So we know that the probability of any given tree being taller than 4.8 is 0.2525. So now we can apply that to the total amount of trees because it's likely that 0.2525 of these trees will be greater than 4.8. So we can say that the number of trees is equal to 4,000, so our total amount of trees, multiplied by our probability that they're taller than that, which gives us, closest to the nearest tree, 1,010 trees. Now don't forget your units, which in this case is trees, because we are in a real world context here, so we need that. Guys, that's our second and final mark for part A. If you have any questions, let me know, but let's move on to part B. Part B says, if a tree is taller than 4.8 meters, the apples picked from it are considered to be top quality. 25 trees are chosen at random from the orchard. All right, so 25 trees greater than 4.8 means that they're top quality, okay? Awesome. Find the probability that at least 10 of these 25 trees have produced top quality apples. Give your answer correct to 4 decimal places. All right, sweet. So immediately we can tell that we're going to need to use our binomial calculator, all right? Because we've got a certain amount of trials. We're looking for the probability that at least 10 of them have a certain trait, and each one of the attempts has the same probability to be top quality, right? So we get out our binomial CDF calculator in our CAS, and it's going to ask us for four things: lower, upper, N, and P. Okay, so our lower is 10, right? Because we're looking for the probability that at least 10 of them have produced top quality. So it could be 10 of them are top quality, 11 of them, 12, 13, 14, all the way up to 25. All right, so our lower is 10 and our upper is 25. Now, how many trees are we taking a sample of? 25. So N is 25, and P is our probability that any one of these is of top quality, right? So it's top quality if it's taller than 4.8 meters, and in part A, we found the probability that it's taller than 4.8 to be 0.2525, right? This might be a little tricky to figure out. We've got to recognize that we have to link back to part A. So now so that's actually our first mark, recognizing all that. And then our second mark comes from our answer. So putting that into our CAS, we get the probability that x is greater than or equal to 10, which is equal to 0.0755. 6. That is our second and final mark for part BI. That was BI actually. Yep. So that's it. Let's move on to part BII. Part BII introduces our concept of conditional probability here, right? So we've got BII, and that is 2 marks. So it says, it is found that at least 10 of these 25 trees have produced top quality apples. Find the probability that less than 13 of these trees produce top quality apples. All right, awesome. So what we're essentially saying is that we're trying to find the probability that less than 13 of them produce top quality apples, given that at least 10 of them did, right? Because we're saying that we know that 10 of them did, or sorry, at least 10 of them did, which is our given. Okay, so that's a given that we have to kind of recognize. Now, according to our given formula, or our conditional probability formula, this given this is equal to this intersect this over this. So the probability that x is less than 13 intersect x is greater than or equal to 10 over the probability that x is greater than or equal to 10. Fantastic. So now we just need to find our intersects, right? So I'm just going to rewrite this as the probability that x is between 10, including 10, and less than 13. Probability that x greater than equal to 10. Fantastic. So now we've actually got this situation where we can use our binomial distribution again, okay? So whenever we have questions like this, it's binomial distribution, right? So we're going to pull out our binomial CDF in our CAS. And again, as always, you're probably getting really sick of me doing this, but if you're watching it, it's probably for a good reason. So lower, upper, N and P, where our lower bound for our, we're going to do this one by one. So we've got this one first, and then we'll do this one. So our lower bound is 10, because we're including 10, and our upper bound is not 13, because we're not including that. It's less than 13, which means our upper has to be 12. Okay, so it's the whole number before it. N is still 25. We've still taken 25 of the trees. And P is still our 0.2525, which we found in our part A, which was the probability that it was greater than 4.8 meters. Awesome. So plugging this into our CAS, we get between 10 and 13 is equal to 0.0719. And plugging our... Actually, sorry. We've already found that the probability of x is greater than or equal to 10 is equal to 0.0756. We found that in part BI. So there's a lot of linking going on here, which is why these questions might be a bit tricky. So therefore, the probability that x is less than 13, given that x is greater than or equal to 10, equals this over this. So 0.0719 over 0.0756 equals 0.9510. And this is our second mark. I didn't actually write down our first one. This is our first one. So our second mark happens there, 0.9510. And guys, that's it for part BII. Let's move on to part C. Part C says, naturally, different areas of the orchard have different acidity levels in the soil. The distribution of acidity levels throughout the orchard measured by pH is modeled by a continuous random variable x with the probability density function given by this. Find the probability that a random soil sample has an acidity level of 7.25 pH or higher. All right, awesome. So again, guys, whenever we deal with continuous probability with probability density functions, the probability is the area under the graph. Okay, so that those two things are linked intrinsically. So we're looking for the probability that x, which is the acidity level, is greater than or equal to 7.25. That's what we're looking for. Which means that we're looking for the area under the graph from 7.25 onwards, right? So we're looking for the area, which is the probability. And how do we find area under a graph? Using our integrals. So we're looking for the area from 7.25 onwards, but not to infinity because our function is limited, right? It has an upper limit of 15 on 2. So we say that our upper limit is 15 over 2, and our function is just whatever our function is. So negative 6x squared plus 84x take 585 on 2 dx. So now what we get is negative 2x cubed plus 42x squared take 585x over 2 from 7.25 to 15 on 2. This is our first mark. Second mark comes from evaluating all this and try and do as much working as you possibly can. So sub in all of this stuff. So we get -2 outside of 15 on 2 cubed plus 42 15 on 2 squared minus 585 15 on 2 over 2 minus everything with 7.25 in it. So 7.25 cubed plus 42 7.25 squared minus 585 7.25 over 2, which all equals 0.1563, which is our final answer and our second mark. So guys, that's it for part C. Let's move on to part D. Part D is very similar to part C, except almost the opposite, if that makes sense. So it's a 2-mark question again. And we're asked to, well, we're told the orchard has a total area of 10,000 square meters. 4,000 square meters of orchard have a pH level of K or less. Okay, so 4,000 out of the 10,000 has a pH of, the pH is less than K. Okay, or less than or equal to K, I should say. So we're trying to find this value of K. So we know that the probability that any given piece of soil has a pH of, we know that the probability of any given piece of soil having a pH of less than K is equal to 4,000 on 10,000. Okay, so that means that our probability, which is 4,000 in 10,000, is equal to the area under the graph from our lower bound, which is 13 on 2, to K. Okay, because we're dealing with less than K, which means that everything less than K until 13 on 2 is our area. From -6x squared plus 84x, take 585 on 2 dx. Awesome. Now simplifying this, what we get is 4,000 on 10,000 can simplify to 2 on 5, and that equals -2x, -2x cubed plus 42x squared. Take 585x on 2 from 13 on 2 to K. So 2 on 5 equals this. And what we're going to do now is just sub in our values for K and 13 on 2. So we get -2K cubed plus 42K squared, take 585K on 2, minus -2, 13 on 2 cubed, plus 42, 13 on 2 squared, take 585, 13 on 2 over 2. Awesome. And that's it. So what this simplifies down to, actually that's our first mark. What this simplifies down to is 0 equals -2k cubed plus 42k squared. Take 585k on 2 plus 3378 on 5. Now, I could go through all of this working, but I don't want to because you're going to get bored, and I don't want you to get bored watching these videos. So we can solve for k and Kaz now. And we end up with, can you see that? Yep. So we end up with k equals 6.1695, k equals 6.9329, and k equals 7.8976. Now, k has a restriction, right? Because k is actually one of our x values. So x is between 13 on 2 and 15 on 2, which is actually the same as 6.5 to 7.5, okay? Now, the only one that's between 6.5 and 7.5 is 6.9329, which means that k is equal to 6.9329. That is our second and final mark for part D, guys. As always, let me know if you have any questions, but let's move on to part E. Part E should be quite straightforward as long as you remember the mean formula. So part E tells us to find the mean of x. All right, this is just a 1-mark question, so we can simply chuck it into our Kaz and write the answer down. But the important thing to note is that the mean of a continuous probability density function is equal to the lower to the upper of x times f of x dx. Okay, so our lower is 13 on 2, upper is 15 on 2, x times our function, which is negative 6x squared plus 84x, take 585 on 2 dx. And again, because this is a 1 mark question, I would just sub this all into your CAS, and what it spits out is 7. So our mean of x is 7. Guys, that's it for MM406. As always, if you have any questions, please let me know in the comments below. I'd love to help you out if you're struggling with anything. But yeah, apart from that, thank you very much for watching this video, and I will see you in the next one.